Okay, here's a discussion of homework set 9 from, well, it's sections 34 through 42, as the sections are numbered in the 9th edition of the book. But you're asked in 3.34.3, find Z1 and Z2 such that the principal branch, principal value if you like, principal value of the logarithm of Z1, Z2 does not equal the sum of the logs. A little bit of a typo there. Okay, so how can you violate this? Well, probably with some stuff we've done in the past already. With arguments, we've seen the principal argument of the product is not necessarily the sum of the principal arguments. Principal arguments are what? Between negative pi and pi. So the principal branch of the logarithm, or the principal values of the logarithm, are going to involve arguments between negative pi and pi as well. So if you could find maybe some complex numbers such that when you add these arguments together, you don't get something between negative pi and pi, you're good to go to violate the equality. Number 3.36.2 asks for the principal value of e over 2 negative 1 minus the square root of 3i to the 3 pi I power, complex base, complex exponent, branches of the logarithm are underneath this, principal value, principal branch. Okay, it's really a matter of finding the argument, the principal argument of this complex number, and using the definition of z to the c power, if you like. So we've got a complex number to a complex power. My only hint on this one is use that definition of z to the c power. And hey, the argument of this is a special angle. I see a 1 and a square root of 3. So yeah, I think we've got some special angle stuff going on there. The e over 2 doesn't really affect anything in terms of arguments in this one. The graduate problem, 3.35.5, the principal nth root of z sub 0 we defined as this. Theta sub 0 is the principal argument. This was a definition we had originally back when we encountered principal branches. This is a division there. So we take the principal argument, divide by n, multiply by I, put that in an exponential. This is how we found principal nth roots initially, back when we were computing roots of unity and roots of complex numbers. But now we've introduced this function z to the 1 over n, and it has principal values because it's based on logarithms as well, based on the principal branch of the logarithm. So the question here is to show that this computation we had back a couple of months ago, this computation and the value of the principal value of the function z to the 1 over n, defined in terms of principal branches of logarithms, show those two things are the same. About all I got is, well, we could take this c sub 0 given up here. We'd write it as mentioned. Might be useful to take this nth root of r. This is just real stuff here. R is the modulus, just an expression of polar coordinates version of this c sub 0. Let's take that nth root of r and write it as e to the natural log of the nth root of r. The exponential and the log cancel. Now we've got an exponential expression for this part and an exponential expression for this part. We got a product of two exponential functions. I think that might be helpful, along with some properties of exponentials, in linking together the c sub 0 value with the principal value of z to the 1 over n. So take that information and follow your nose, and you'll produce what we'd get for the principal value of z to the 1 over n. There's a principal argument right there. Is a big hint. Okay, number 4.42.2 part D says evaluate this improper integral. You're given the condition that real part of z is greater than 0. You're going to need the condition real part of z is greater than 0. If you don't use that, then something's wrong. And what we'll do is, my only real hint is take this improper integral from 0 to infinity and write it as a limit. Limit as b approaches infinity, integral from 0 to b, e to the negative z t dt. The very definition of an improper integral. How you feel about this? Can you find an antiderivative? Remember, you're integrating with respect to t, not with respect to z. And we will or have already done integrals with respect to z. But you'd need an antiderivative with respect to t for this. I think you'd be good to go on that. Find that antiderivative, plug in the bounds, and then evaluate the limit. And keep in mind, this fixed number z has real part positive. Somewhere in there, you're going to have an e to the negative real number t. And when t approaches infinity, which will ultimately be the case when you do the substitutions with the bounds, that exponential function, because of the negative sign, will go to 0. So a piece of something is going to 0. The imaginary part, there's probably some oscillations. But take an antiderivative, plug in the bounds, use this information, and you're good to go. And the last one says, 4.42.4, here's two versions of the same integral. We're integrating from 0 to pi e to the 1 plus I x dx, and they've broken it into real and imaginary parts. So we've got a real integral plus I times another real integral. So it's integrals of real and imaginary parts. And the instructions are, evaluate the two integrals on the right by evaluating the integral on the left. Okay, in this case, x is the variable with which we're integrating with respect to. We're good to go with our current information if we can find an antiderivative. Find an antiderivative. We're dealing with nice functions and all this. These things are exponential functions when we've had the antiderivative conversation. Sure, this is the antiderivative. Differentiate with respect to x, and you'll see this is the right choice. So all we've got to do is take the antiderivative, plug in the endpoints. That will produce for this integral on the left a complex number with a real part and an imaginary part. Well, the real part is going to equal this integral, and the imaginary part will equal that integral. Write out some explanation along those lines, show those computations, and you're good to go. And then so goes homework number 9.